Sound garbage collection for C using pointer provenance. Software systems are developed using C and C++ in many application domains, ranging from operating systems, web and database servers, productivity software, etc. However, these languages do not provide a managed memory, so these systems can suffer from reliability issues and their security can be compromised via memory safety attacks. An unmanaged memory raises three problems. It requires programmers to explicitly manage memory, and reasoning for such can be challenging and error prone. As a result, it can cause runtime violations of temporal memory safety, leading to bugs such as use after free. Checking against such memory safety errors incurs high overheads. And finally, inefficient memory management can lead to memory leaks, impacting the reliability of these systems. Now, while modern C++ with smart pointers and Java mitigate some of these problems, it is not enough because C and C++ continue to be a popular choice for software development. C remains the top choice among languages used in industrial software, and Google search trends indicate interest in C has remained quite high throughout the years. Besides, a large body of legacy systems written in C are still in use. Garbage collection for C and C++ can address these problems. By automatically reclaiming unreachable objects from memory, it relieves the programmers from reasoning about memory, it enforces temporal memory safety, and avoids memory leaks. However, prior garbage collectors for C and C++ are unsound for legal C programs. In this work, we solve this using a new technique, dynamic pointer provenance tracking. To make pointer provenance tracking efficient, we optimize using optimistic hybrid analysis, a combination of profiling and static analysis to improve dynamic analysis. And we realize a solution with average 16% tracking overhead. So let us understand how current garbage collectors for C and C++ work, and as we will see, they can unsoundly collect reachable objects even for standard compliant C programs. Garbage collectors compute the set of all reachable objects at an instance of runtime and then free up memory by reclaiming unreachable objects. Starting with a root set of locations, they first identify all pointers, then they follow these pointers to their referent objects and mark them as reachable. This continues iteratively until no more reachable objects can be found. Finally, a sweep phase reclaims memory from the unreachable objects. So garbage collectors need two important pieces of information. When a reachable object is found, the pointers within information locates the set of pointers within the object. The points to information identifies which objects these pointers point to. Now, prior garbage collectors compute these two using a value-based approach, which is unsound. For C and C++, in the absence of strong typing and without runtime type information, how do we know if it is a pointer? Prior value-based garbage collectors use a reasonable heuristic. They scan through locations looking at their values. If the value is within the range of a currently allocated heap object, it is assumed to be a pointer, and the referent object is identified using the pointer's value. So this inherently assumes pointers being in bounds. This is problematic as it cannot discover reachable objects when pointer information is held, but the pointer value is not in bounds. Therefore, it may free reachable objects. This can happen in legal standard compliant C programs, as pointer values can be taken out of bounds by casting them into integers and manipulating them using arbitrary arithmetic. Let us look at an example to understand this soundness problem. The figure illustrates a typical representation of a doubly linked list with a next and previous pointer for each node. Now, in memory constrained environments, an XOR linked list can save space by storing the XOR of the next and previous pointers in a single location. Traversal can begin in either direction at the head or tail and proceed by recovering the next pointer via XOR operations. Note that this can be implemented in a standard compliant C program. Note that none of the internal nodes store a literal pointer value, but they encode sufficient information to reconstruct two pointers. In fact, looking at the middle node, the literal value of C's pointer is not stored anywhere in the program state, but it can be reached using the XOR traversal method. A purely value-based garbage collector would miss this node and may incorrectly collect it. So the problem is to precisely identify at runtime which values hold pointer information rather than literal pointer values. So instead of scanning for pointer values, what if we track the pointers using information flow tracking? This is the idea behind pointer provenance tracking. To identify pointers within, explicitly keep track of all pointers, and to identify points to, track the referent objects along with the pointers. The key insight is programs cannot create pointers out of thin air. They must be derived from allocation function returns. So with these well-defined sources, we can track pointers using information flow tracking by properly defining taint propagation rules. Initially, all values have empty pointer provenance. Upon allocation, we attach the object ID to the returned pointer. The example highlights the pointer variable, indicating that it is now tainted with a pointer. From there on, we follow the propagation of pointers through all operations. They can propagate via explicit data flow. For example, when pointer is used to compute x, the pointer taint is propagated to x. Alternatively, pointers can also propagate implicitly via control flow dependence. For example, if the check on x's value succeeds, y holds the value of pointer even though it has no data flow dependence to pointer. So for soundness, y should carry the pointer taint as well. Note that integer typed values x and y become tainted as pointers. We will use the term pointer to refer to not just pointer typed values but all pointer derived values. Tracking pointers in this manner would enable the garbage collector to soundly identify all pointer information at runtime. But how to do this efficiently? Information flow tracking is known to incur slowdowns, and indeed, our results show that a naive implementation of data flow pointer provenance tracking slows down by up to 8 times. But we can optimize using static analysis, and we identify several static analysis opportunities to optimize pointer provenance tracking. So first, let us look at the optimizations for explicit data flow tracking. First, to track all pointers, we need a single bit taint attached to all values to discover what values are pointers. The insight here is that most operations do not change the pointer taints of their operands, and static analysis can elide them. So majority of instructions operate on non-pointers that will never hold pointer taints. Most instructions dealing with pointers operate on statically declared pointers, which can be thought of as being always tainted. So all these operations do not require tracking. Only when a pointer value flows to an integral value via casting, we need tracking to transfer the pointer taints. Now, if we were merely concerned about tracking pointers, we are all done. But remember that we also need to explicitly track the referent objects along with the pointers, since pointer values can go out of bounds. Now, we define pointers to be safe that have two important properties. They are provably in bounds, and they have singleton provenance, that is, they can be used to only point to a single object. For these safe pointers, their values derive their points to object, and we don't need additional tracking. Now, pointers can become unsafe in two ways. Via pointer arithmetic, they can go out of bounds, and via partial assignments. For example, casting pointer to integer type is not guaranteed to preserve the exact value, making it out of bounds. So the insight is that many pointers do not require explicitly tracking their objects. Only these unsafe pointers require tracking their points to object. Now let us look at one optimization to elide points to tracking for these unsafe pointers. The example program here allocates a new character buffer, and then inside the for loop, iteratively copies from a source buffer. Looking at the first instruction, we can explicitly track the object ID with pointer. Now moving inside the loop to the pointer plus offset operation, as soon as we perform arithmetic, the pointer value can go out of bounds and potentially become unsafe. The insight for eliding redundant points to tracking is that pointer operations often do not change the points to object to a new object. In fact, when the operation reassigns the resulting pointer to the same variable, we know that the points to object cannot change. So for this common array indexing operation, we just need the one-time metadata creation operation, and we can elide the tracking operation inside the loop since the taint remains unchanged. Now you might be thinking, is this tracking really necessary? In a correct program, simply incrementing the pointer to the array will not take it out of bounds. And indeed, we can prove it statically by leveraging pointer dereferences. The subsequent dereference tells us that in a correct program with well-defined behavior, its value must be in bounds due to spatial memory safety. Since pointers are rarely manipulated without using them later on, this reasoning can identify many more safe pointers and elide tracking their points to. Another way to identify more safe pointers is to leverage the C standard. The standard induces several restrictions on how pointers may be manipulated, essentially guaranteeing that all values in declared pointer types are always in bounds. So all pointer type values are safe pointers. But since many programs and compilers may not strictly adhere to the standard, We turn this optimization on optionally for standard compliant portable C programs. So these optimizations improve data flow pointer provenance tracking. Now let us consider tracking for implicit control flow. Any implicit leak of information can be potentially harmful in a security or privacy context. However, in the context of garbage collectors, there has to be sufficient information leaked to be able to reconstruct pointer values. And we reason that most common pointer comparisons do not leak sufficient information to reconstruct pointers exactly. A very common pointer comparison is checking for null. This comparison reveals a single bit binary information about the pointer being null or non-null, and this is obviously insufficient to recreate a valid pointer. Another common operation is comparing two pointers. Once again, this reveals only one bit information on the relation between the two pointers, and we cannot recreate either pointer without explicit data flow. So these common pointer comparisons do not require implicit tracking. Now the above reasoning holds valid only for in-bounds pointer comparisons. For example, if you compare an out-of-bounds pointer derived value, you can reveal sufficient information to later reconstruct a pointer. For example, say pointer diff stores the XOR of two pointers. If the equality comparison with a known constant succeeds, one can later recreate pointer 2 only using pointer 1. So we must ensure that the compared pointers are in bounds, but this is hard to check statically. Here, we use a recent program analysis technique called optimistic hybrid analysis. We statically assume that compared pointers are in bounds and elide the implicit tracking, resulting in an optimized analysis that we call the fast path. Then we instrument dynamic checks along the fast path that check whether the pointers are actually in bounds. Execution continues in the optimized analysis as long as the checks hold. If a dynamic check ever fails, we can switch to a slow path using conservatively optimized analysis with all implicit tracking operations and continue. Since programs do not commonly perform comparisons on out-of-bound pointer-derived values, the analysis remains in the optimistic fast path. This technique of assuming an invariant to induce static analysis optimization, then checking the invariant dynamically and recovering if failed is called optimistic hybrid analysis. In fact, we heavily make use of this technique in all the previous static optimizations. Our static analysis used data flow analysis and pointer analysis. A traditional sound static analysis over approximates all possible program states and can become very imprecise. But optimistic hybrid analysis uses the insight that the static analysis can be made precise if it only analyzes the set of all dynamically exhibited program states. To this end, it profiles likely invariants from observed executions to predicate the static analysis to a much precise set of program states. In rare executions, the assumed invariants may fail, however, so the dynamic analysis must check for invariant validation and recover the analysis. Previously, optimistic hybrid analysis was used to optimize information flow tracking, and we use this as a basis for our pointer provenance tracking. The ProvGC tool works as follows. First, it profiles the target program on a set of inputs to gather likely program invariants. The static analysis then assumes these invariants, inducing a much precise information flow analysis, and this further uses our provenance tracking optimizations. The static analysis instruments the program with the necessary provenance tracking operations and the optimistic hybrid analysis invariant checks. The provenance metadata tracking uses shadow memory and splay tree organization for efficient tracking. The instrumented program runs along with the runtime garbage collection library, and we modify the Boehm-Demers-Weiser garbage collector to use provenance metadata instead of the value-based garbage collection. This result plots the overhead of pointer provenance tracking normalized to baseline execution without any tracking. For each benchmark, we first plot the overhead of tracking using our static optimizations in a conservative hybrid analysis. The solid portion corresponds to the overhead due to explicit tracking, and the striped portion corresponds to implicit tracking. Implicit tracking in a conservative manner does incur large overheads as seen here. Next, we optimize using optimistic hybrid analysis. This yields significant reduction in overheads from around 700% to 59% on average. The next two bars performs the conservative and optimistic analysis, this time additionally using the optimization induced assuming the C standard. This brings down the overhead to an average 16%. Provenance-based garbage collection also improves on the efficiency of each garbage collection run. The figure plots the collection time of a single invocation of ProvGC normalized to that of BDWGC. On average, ProvGC collects 13% faster, primarily because it avoids scanning large objects and directly queries the metadata in order to discover pointers. The figure on right plots the fraction of memory retained after a single invocation of ProvGC compared to BDWGC. In addition to being sound, ProvGC tracks pointer information precisely, whereas value-based garbage collection can mistake regular values to be pointers. As a result, ProvGC reclaims around 4% more memory on average. To summarize, prior value-based approaches for garbage collection are unsound for a weakly typed language such as C. They can fail to discover reachable objects when pointer values are out of bounds and thus free them incorrectly. Our solution uses dynamic pointer provenance tracking to explicitly track pointer information at runtime, which provides a way to realize a sound garbage collector for C. We optimize this using optimistic hybrid analysis to realize pointer provenance tracking with 16% overhead for standard compliant C programs.